Hello, and welcome to Boring History for Sleep. Tonight we will be exploring a topic of quiet, foundational importance. Imagine a city engulfed in flames. It is the early morning of February 7th, 1904, in Baltimore, Maryland. A fire that started in a dry goods warehouse is now an uncontrollable conflagration. As the city's own fire departments are overwhelmed, urgent telegraphs summon help from neighboring cities. Soon, special trains are racing towards Baltimore, carrying steam-powered fire engines and determined firefighters from Washington, D.C., from Philadelphia, from Wilmington, and even from New York. They arrive, a hopeful cavalry, ready to pump millions of gallons of water onto the inferno. But as they unroll their hoses and approach the Baltimore hydrants, a dreadful and simple problem becomes apparent. The threads on their hose couplings do not match. They cannot connect. Their powerful engines, full of potential, are rendered useless by a few millimeters of mismatched brass. To truly understand this frustrating and overlooked chapter of civic engineering, we must turn back the clock and examine the very threads of the problem. The story of the standardization of fire hose couplings in the United States is not a story of a single, brilliant invention or a dramatic moment of discovery. Instead, it is a slow, methodical, and often frustrating narrative of incremental progress. It is a story of committees, of meticulous measurements, of persuasion, and of the gradual, unglamorous work of building a system of safety. It is a history written not in grand declarations, but in the fine print of engineering specifications and the minutes of long-forgotten conventions. To begin, we must first appreciate the world before any form of standardization existed. In the early to mid-19th century, firefighting was an intensely local affair. Most cities and towns were protected by volunteer fire companies, which were as much social clubs as they were emergency services. These companies often competed with one another for prestige, for the honor of being the first to arrive at a fire, and for the most impressive equipment. A company's identity was tied to its fire engine, a beautifully painted hand pumper, or, later, a gleaming steam pumper. And every piece of that equipment, from the engine itself to the leather hoses and their brass couplings, was often sourced from a different manufacturer. There was no central authority dictating how these components should be made. A foundry in Philadelphia might produce a fire engine with one set of specifications for its outlets, while a manufacturer in Cincinnati produced another. The makers of the hoses and couplings, in turn, created their own proprietary designs. This was not born of malice or a desire to create chaos. It was simply the natural state of a decentralized competitive market. Each manufacturer believed their design, their specific combination of thread pitch and diameter, was superior. It was a point of pride, a feature to be advertised. A slightly coarser thread might be claimed to connect more quickly, while a finer thread might be marketed as providing a more secure, leak-proof seal. The couplings themselves were marvels of brasswork. The two primary parts are the male coupling, with its external threads, and the female coupling, with its internal threads, and a rotating swivel to allow it to be tightened without twisting the entire length of the hose. On the exterior of the female swivel were lugs, protrusions that allowed firefighters to get a firm grip with a spanner wrench to tighten the connection. Early designs featured a simple pin-style lug, which was effective, but could sometimes catch on obstacles as the hose was dragged through the streets. In this environment, a city like Boston might have dozens of different fire companies, and it was entirely possible that within that single city, several different, incompatible hose thread patterns were in use. A company in the North End might use a coupling made by one manufacturer, while a company in the South End used another. For fires contained to a single building, this was a manageable, if inefficient, reality. But as American cities grew larger and more densely packed with wooden structures, the potential for disaster scaled accordingly. The first significant, large-scale demonstration of this systemic vulnerability occurred on November 9, 1872. This was the Great Boston Fire. Less than a year after the infamous Great Chicago Fire, a blaze broke out in a commercial warehouse in downtown Boston and quickly spread. The fire was ferocious, overwhelming the capacity of the Boston Fire Department. Just as in Baltimore 3 decades later, calls for mutual aid were sent out. Fire companies from as far away as New Haven, Connecticut, and Manchester, New Hampshire, loaded their steam pumpers onto railroad flat cars and rushed to assist. They arrived to a scene of chaos and discovered the same paralyzing issue. The hose couplings from Worcester, from Providence, from all the surrounding towns did not match the threads on the Boston fire hydrants. They could not connect their pumpers to the city's water supply. In some cases, responding companies couldn't even connect their hoses to the outlets on Boston's own fire engines to act as relay pumps. Desperate firefighters tried to find solutions. They wrapped the mismatched threads in sailcloth and leather, hoping to create a friction seal, but the immense pressure from the steam pumpers simply blew these makeshift connections apart. Some accounts tell of blacksmiths being summoned to the fire lines in a futile attempt to reforge couplings on the spot. The result was a tragic display of impotent power. Dozens of the nation's most advanced firefighting machines stood idle, sometimes just feet from a hydrant, while a significant portion of the city's commercial heart burned to the ground. The Great Boston Fire served as a stark and costly lesson. In the aftermath, the fire service community began to take the issue of non-standard equipment seriously. The newly formed International Association of Fire Engineers, or IFR, which would later become the International Association of Fire Chiefs, made the topic a recurring subject of discussion at its annual conventions. The problem was clear, but the solution was anything but. The first step was to understand the scope of the problem. The IAF and other concerned bodies began to conduct surveys. They wrote to fire chiefs across the country, asking for the specifications of the couplings used in their departments. The responses that trickled in painted a picture of pure chaos. They discovered that there were not 10 or 50 or even 100 different standards in use. There were over 600. These variations were often minute, yet completely effective at preventing a connection. A coupling might have a diameter of 3 inches, but with 8 threads per inch. Another might also be 3 inches in diameter, but with 7.5 threads per inch. A third might have the correct thread pitch, but a diameter that was off by a mere 1/16 of an inch. Each of these was, for all practical purposes, a unique and incompatible system. Some cities, like New York, had their own long-established and deeply entrenched thread patterns, used on thousands of hydrants and tens of thousands of lengths of hose. The idea of replacing all of that expensive equipment was, to a city comptroller, a non-starter. The resistance to standardization was not just financial. There was also a great deal of professional pride and regional stubbornness involved. A fire chief in St. Louis might be perfectly happy with his department's St. Louis standard couplings and see no reason to change to a system championed by engineers from New England. Manufacturers, too, had a vested interest in maintaining their proprietary systems. It created a captive market. If a fire department bought hoses and couplings from a certain company, they were likely to continue buying from that same company to ensure compatibility with their existing stock. Throughout the 1870s, 80s, and 90s, the debate continued. Committees were formed within the IAFE, papers were presented. Engineers debated the optimal thread angle, the ideal number of threads per inch for a balance of speed and security, and the most durable alloy for the brass. Several recommended standards were proposed, but they were just that, recommendations. There was no body with the authority to enforce a single standard across the nation. Progress was minimal. A few neighboring towns might agree to standardize amongst themselves to facilitate their own local mutual aid agreements, but a national solution remained elusive. The memory of the Boston fire began to fade, and the immense cost and logistical complexity of a nationwide conversion seemed to outweigh the perceived risk. While the fire chiefs debated, another powerful force was taking note of the problem: the fire insurance industry. For insurance underwriters, large urban fires were a catastrophic financial risk. They had a direct and compelling interest in improving fire protection and prevention. The National Board of Fire Underwriters, or NBFU, was established in 1866 to, among other things, collate fire data and promote practices that would reduce fire losses. By the late 19th century, the NBFU's engineers were conducting detailed inspections of city fire departments and water supply systems. And in their reports, the issue of non-standard hose couplings appeared again and again as a critical deficiency. The NBFU had a powerful tool at its disposal: money. The insurance rates that a city's residents and businesses paid were directly influenced by the NBFU's assessment of that city's fire risk. A city with a well-equipped, well-trained fire department and a robust water system would be given a better grade, leading to lower insurance premiums for everyone. The NBFU began to make it clear that the lack of standardized couplings would be a significant negative factor in their evaluations. This applied economic pressure where mere persuasion had failed. City governments might ignore their fire chiefs, but they could not easily ignore a decision that would raise insurance costs for every voter and business owner. One of the key figures in this period was an engineer named John R. Freeman. In the 1890s, Freeman conducted an exhaustive study on behalf of the factory mutual insurance companies. He meticulously documented the chaos of non-standardization and championed the idea of a single national standard. He argued that the ideal standard should not be a brand new, theoretically perfect design, but rather the one that was already in the most common use, thereby minimizing the number of cities that would need to make a change. His work laid much of the technical and philosophical groundwork for the solution that would eventually be adopted, but it would take another national catastrophe to provide the political will for real action. That catastrophe was the Great Baltimore Fire of 1904. If the Boston Fire was a wake-up call, the Baltimore Fire was a blaring, inescapable siren. The fire burned for over 30 hours, destroying more than 1,500 buildings across 70 city blocks. The arrival of fully equipped, yet incompatible fire apparatus from Washington, Philadelphia, and New York was not just a footnote to the disaster. It became a central part of the story, reported in newspapers across the country. The image of helpless firefighters unable to connect their hoses to a plentiful water supply became a national symbol of dangerous inefficiency. The public outcry and the staggering financial losses, estimated to be over $100 million at the time, created a tipping point. The problem could no longer be ignored or relegated to technical committees. The NBFU, in particular, was galvanized. Immediately following the fire, the NBFU, in cooperation with the American Water Works Association and the IAFE, intensified its efforts. They formed a new joint committee, the Committee on Standard Hose Couplings. This committee did not start from scratch. They built upon the earlier surveys and the work of John R. Freeman. Their first task was to conduct the most comprehensive survey to date. They sent out requests to hundreds of fire departments, asking them not just for the specifications, but for physical samples of their couplings. Soon, their offices were filled with a bewildering array of brass fittings from every corner of the country. They meticulously measured each one: the outside diameter of the male thread, the number of threads per inch, the shape of the threads themselves. The data confirmed what they already knew. The situation was a chaotic mess. However, amidst the hundreds of variations, a pattern began to emerge. A significant number of cities, particularly in the Northeast, were using a coupling on their 2.5-inch hose that had 7.5 threads per inch and an outside diameter on the male thread of 3 1/16 inches. While it was by no means a majority, it was the most common single pattern they could find. Adopting this pre-existing, widely used pattern was a crucial strategic decision. It followed John R. Freeman's logic that the best standard is the one that requires the least amount of change. For the cities already using this pattern, conversion would cost nothing. For others, the change would be necessary, but the committee was choosing the path of least overall resistance. In 1905, just a year after the Baltimore Fire, the committee formally proposed their standard. For the workhorse of the fire service, the 2.5-inch hose, the standard would be 7.5 threads per inch with a 3 1/16 inch outside diameter. For other hose sizes, such as the 1.5-inch and the larger 4.5-inch suction hose, similar specifications were proposed based on the most common existing patterns. This set of specifications was formally adopted by the National Fire Protection Association, or NFPA, and became known as the National Standard Thread, or NST. Sometimes it was also referred to as National Hose Thread, or NH. Having a standard on paper, however, was only the first and perhaps the easiest part of the solution. The real challenge lay in implementation. How could they convince thousands of individual, self-governing municipalities to spend the time, effort, and money to convert their equipment? The federal government had no authority to mandate such a change. The process would have to be one of voluntary adoption, driven by a combination of education, technical assistance, and economic incentives. This began the long, slow, and methodical phase of the standardization effort, a process that would occupy the next several decades. The NFPA and NBFU launched a nationwide campaign. They published pamphlets and articles in firefighting journals, explaining the importance of the standard and the lessons of Boston and Baltimore. They sent speakers to fire chief conventions and city council meetings to make the case for conversion. One of the most significant barriers was, of course, the cost. A city might have thousands of fire hydrants, hundreds of outlets on its fire engines, and tens of thousands of feet of hose, all with non-standard threads. The prospect of replacing all of this at once was financially impossible for most communities. This is where the engineering ingenuity of the standardization movement truly shone. They realized that they didn't need to replace everything. It was possible, in many cases, to modify the existing equipment. To this end, the NFPA, in collaboration with the American Society of Mechanical Engineers and the National Bureau of Standards, developed a set of special tools. These were essentially large-scale taps and dies. A tap is a tool used to cut internal threads, like those inside a hydrant outlet or a female coupling. A die is used to cut external threads, like those on a male coupling. These tools were designed to be used in the field. A team of skilled mechanics could travel from city to city with a set of these standardization tools. They could go to each fire hydrant, attach a special jig, and use the large tap to recut the existing threads to the new national standard. Similarly, they could clamp a male hose coupling into a device and use the die to rethread it. This process was far cheaper and faster than wholesale replacement. It was a brilliant, practical solution to a massive logistical problem. The National Bureau of Standards, the federal agency responsible for weights and measures, played a vital role in this. They created the master gauges for the national standard thread. These were perfectly machined and precisely measured reference couplings, against which all other manufacturing tools and final products could be checked. This ensured that a standard coupling made in a factory in Ohio would be identical to one made in New York. The Bureau's authority and precision lent an essential layer of legitimacy and reliability to the entire effort. With a standard defined and a practical method for conversion established, the NBFU could now apply its financial leverage more effectively. Their engineers, when grading a city's fire defenses, would now specifically check for compliance with NST. A city that had converted, or was actively in the process of converting, would see its rating improve. A city that refused to adopt the standard would be penalized. The prospect of lower insurance premiums became a powerful motivator for mayors and city managers to approve the expenditure for the rethreading program. The process of adoption was a slow grind, city by city, fire department by fire department. It was not a sweeping national reform, but a piecemeal campaign. In the 1910s and 1920s, NFPA field engineers traveled the country, acting as advocates and consultants. They would arrive in a town, meet with the fire chief and the mayor, explain the benefits, and demonstrate the rethreading tools. They would help the city conduct a survey of its own equipment to determine the scope of the work needed. The work itself was meticulous. Firefighters and public works employees would spend weeks or months working their way through the city's water system. Every single fire hydrant nozzle cap had to be removed, the threads checked, and if non-conforming, re-tapped. The outlets on every pumper had to be addressed. Every length of hose, both on the engines and in reserve at the firehouse, had to have its couplings inspected. Male ends were recut with the die. Female swivels sometimes had to be replaced entirely, as retapping them was more complex. It was repetitive, unglamorous work, but with each hydrant and each coupling converted, the nation's fire protection network grew stronger and more interconnected. The entry of the United States into World War I provided another impetus for standardization. The federal government, concerned with protecting vital war industries and military facilities from fire and sabotage, took a keen interest in the interchangeability of firefighting equipment. The need for a standardized system for civil defense was obvious. The war effort helped to accelerate adoption in many industrial cities. Progress could be tracked in the NBFU's reports. In 1905, only a small fraction of American cities used what would become the national standard. By the 1920s, surveys showed that thousands of municipalities had either fully converted or were in the process of doing so. The standard was gaining critical mass. New fire apparatus and equipment were now almost universally manufactured with NST couplings from the factory, meaning that cities were now converting through attrition as well. As old, non-standard hose wore out, it was replaced with new, standard-compliant hose. Despite this steady progress, the system was far from perfect. Some major cities continued to hold out. New York City, with its massive and deeply entrenched system using the proprietary New York Corporation thread, never adopted the national standard. The cost of converting its tens of thousands of hydrants and vast quantities of equipment was deemed prohibitive. Instead, the Fire Department of New York invested in a huge inventory of adapters. Every fire engine carried a set of fittings that could convert their threads to the national standard, and vice versa. This was a pragmatic, if not ideal, compromise. Other cities, like Chicago, also retained their own unique standards for many years, relying on similar caches of adapters for mutual aid operations. The Great Depression of the 1930s slowed the rate of conversion, as cash-strapped municipal governments had to postpone non-essential projects. However, federal work programs like the Works Progress Administration, or WPA, sometimes provided the labor for public works projects, which could include the systematic rethreading of a city's fire hydrants, breathing new life into the standardization effort. By the time of the Second World War, the situation had improved dramatically since the turn of the century. The need for robust civil defense in the face of potential enemy attack once again highlighted the importance of standardized firefighting equipment. The Federal Office of Civil Defense strongly promoted NST, and its adoption was seen as a matter of national security. By 1950, the vast majority of towns and cities in the United States were using the national standard thread. A fire engine from a town in rural Oregon could, in theory, travel to a city in Florida and successfully connect to a hydrant. The dream of national interchangeability was, for the most part, a reality. Let us pause to consider the quiet, monumental nature of this achievement. It was accomplished with no central mandate, no act of Congress compelling compliance. It was a victory of persuasion over edict. It was the result of a diverse coalition of interests: fire chiefs who wanted to do their jobs more effectively, insurance companies who wanted to reduce their financial risk, engineers who sought rational and efficient systems, and government agencies that provided the technical framework. The story is not one of grand heroes, but of diligent, patient individuals. It is the story of the NBFU engineer traveling by train to a small town in the Midwest to explain the benefits of a 7.5 thread per inch standard to a skeptical city council. It is the story of the mechanic in a municipal workshop, carefully aligning the rethreading die on a brass coupling, slowly turning the handles, watching as new threads are cut over the old ones. It is the story of the committee member, sitting through hours of meetings, debating the precise tolerance for the outer diameter of a nozzle fitting. This process of standardization touches upon many aspects of American civic life. It reflects the tension between local control and national interest. Each town's fire department was a point of local pride and autonomy, yet their isolation created a collective weakness. The adoption of NST was a concession of a small piece of that local autonomy for the greater good of regional and national safety. It also illustrates the powerful and often unseen influence of industry and economics on public policy. The pressure from the National Board of Fire Underwriters was arguably the single most important factor in driving the adoption of the standard. The simple economic logic of lower insurance premiums succeeded where decades of passionate speeches at conventions had not. Furthermore, the technical aspect of the solution, The development of the rethreading tools is a testament to a particularly American brand of practical problem solving. Rather than demanding a perfect but impossibly expensive solution, replace everything, the engineers devised an imperfect but highly effective and affordable one. Rethread what you have. This pragmatic approach made the entire national project feasible. Even today, the work is not entirely complete. Pockets of non-standardization still exist. Besides major cities like New York, some older rural water systems may still have hydrants with unique historical thread patterns. Modern fire departments still carry a variety of adapters on their trucks, just in case. They are a physical reminder of the long history of incompatibility and the hard-won nature of the current standard. The modern fire hose coupling itself has evolved. The old pin lugs have largely been replaced by more ergonomic and less snag-prone rocker lugs. Materials have changed, with lightweight aluminum alloys often replacing heavy brass. But the threads, the fundamental point of connection, remain the same. The 7.5 threads per inch on a 2.5-inch hose, a standard conceived in the wake of a disaster and painstakingly implemented over half a century, continues to be the silent, reliable backbone of the American fire service. When we see a fire engine connect to a hydrant today, the action appears simple, almost trivial. A firefighter grabs a large wrench, spins the coupling a few turns, and in seconds, a secure connection is made. Water flows. This simple act is the endpoint of a long and complex historical process. It is a quiet testament to the lessons learned in the ashes of Boston and Baltimore. It is a monument to the unglamorous but essential work of creating order out of chaos, one thread at a time. It is a story not of revolution, but of a slow, steady, and deliberate evolution, a gradual tightening of the bonds of mutual aid, and a shared system of safety that protects us all, often in ways we never see. And so, the legacy of those committees, those engineers, and those patient mechanics lives on, not in a museum, but in the functional, reliable, and utterly ordinary brass and aluminum couplings found in every firehouse across the country, ready for a call that everyone hopes will never come. The quiet click and tightening of a standardized thread is the subtle sound of a lesson well and truly learned.